Yeah, we do have some pre-trained techniques on the other side. There is a pre-trained model in Hugging Face API. You can explore that as well. I can share you those links maybe after the session. Lalit is asking about the collab notebooks for Contrastive Learning. Yes, you can use collab notebooks. Again, but there is a limitation in collab notebooks. I guess if the limited, if you cross that limitation, I guess you won't be using GPU. But I prefer you to use Kaggle notebooks because that will be super easy to train the models on GPU. I personally use Kaggle notebooks if in case I wanted to train my model on GPU than Collab. But if you're comfortable with Collab, please go ahead with that. Thank you, Tamil. Tamil that's fine. Thank you. Yeah, Lalit, true. Both have some limitations, but depends upon you, like which is more suitable for you. Uh, so George is asking about what? Okay, so George, this is not a demo workshop. Basically, I'll try to cover all the aspects of contrast to learning. I'll also walk you through the code because I have
Sir,
done some kind of just a
sir,
minute.
can you, sorry to
Yeah,
interrupt. Sir, can you
yeah,
try once again?
yeah, sure, definitely. Yeah, I'm able to share my screen now.
Yeah,
Thanks. I'm not
sorry
sure
for
what went
the,
wrong.
yeah, sorry for the problem. Actually, this is the first time I am hosting the meeting, so that's no problem, I think.
No
Sorry.
issues, no issues,
Yeah,
not a problem at all. So,
yeah,
yeah, just a minute.
yeah.
I'll just share my screen. Let me know if in case you're able to view my screen or not. Can somebody, because I couldn't see the chat, please unmute yourself and let me know if in case you're not able to see my screen. Tejas, can you confirm? Tejas, can you hear me? Yes, we can. Thank you. Thank you. Not an issue. So I'll just start from the beginning. Sorry for the issues. So thank you everybody. Thanks for joining this session. In this session, I'm going to talk about contrastive learning for image classification. In this session, we're going to see how the contrastive learning helps us to improve the model performance in image classification. So before jumping into the topic, sorry if I cough in between. I'm having a sore throat. So before jumping into the topic, my name is Ashok. I'm a senior data scientist at PayPal. I have around 8 years of experience in machine learning and data science, and I majorly deal with predictive analysis, recommendation engine, natural language processing, and computer vision. And I'm currently pursuing my master's from IIT Jodhpur. So coming to the table content, here in this session, we're going to see a brief about contrastive learning concept, and we will see the training procedure involved in that. And also I'll introduce you a new loss called contrastive loss, because so far we have seen a cross entropy loss for classification, but in this session, I'll introduce a new loss called contrastive loss, followed by a code walkthrough. And in the end of the session, we can have a Q&A as well. So coming to the contrastive learning, so contrastive learning is a representation of a data in a such a way where the similar data points will have a similar representations, and the dissimilar ones will have a different representations in the embedding space. For example, when you take an image classification where you have two different classes, class one is cat and class two is dog. Now, if you apply contrastive learning on top of the data we have and come up with certain representations, and if you want to compare these representations of data points under class cat, then you will see a certain similarity between these two representations. But when you try to compare the representations of a cat with the representations of a dog, you will see there is a huge difference between these two representations. So ultimately, contrastive learning is trying to pull the data points together, those who are having a similar representations, and also it will push the data points far from each other whose representations are totally different. So by doing that, it will be easy for us to cluster the data points or classify the data points, because we are having a totally different representations based on different clusters or different classes. So now we understood that using these representations, it will be easy for us to perform some downstream tasks like classification or clustering or image detection or segmentation. But the question raises, like, how exactly we can create these representations? Now, let's take an image into consideration. Let's take a cat image and call it as an anchor. And also assume that this image has been taken from a certain cluster. Now, we will transform this particular image into two different images by applying a transformation called T and T dash. So when I say a transformation, you can assume it as a kind of augmentation. So you can apply any kind of augmentation like a flip, rotation, or blur. So you can apply any kind of augmentation, but our ultimate goal is to create two different images from a single anchor, which we have. So basically, this is the anchor, and these two are the augmented images. So once you have the augmented images, then we pass those augmented images to a certain function called f. So when you pass these augmented images to the function, the function f will give us an output called h sub I and h sub j. So h sub I and h sub j are the representations of these two images. So now once we have the representations, we pass those representations to the another function called z. And also z will also give us output, let's say z sub I and z sub j. So now once you have these representations, and now our ultimate goal is to improve the similarity between these two representations. Sorry. So when you try to improve the similarity between these two final representations, then our representations will be so similar for those images which are drawn from a single particular cluster or single particular class. Since these two images are drawn from a single anchor, when we try to improve the similarity between these two particular images, when we try to increase similarity between these two representations, then the representations of these two particular images will be so similar. So coming to the function f is nothing but resnet. So I guess most of you guys might know about this. So this resnet actually will be used to train our classification models. It gives certain embeddings for us or a kind of features. So function f is a resnet, and function z is a MLP, which is a multi-layer perceptron. So now what happens when we pass the images to the ResNet? ResNet gives certain representation based on the pre-trained information it has, and this information will be passed to the multi-layer perceptron, and multi-layer perceptron will give us another set of representation, and finally we try to increase the similarity between these two. In such cases, during that process, our weights of multi-layer perceptron and ResNet will be adjusted in a such a way where the representations will be so similar for those images who are having who are who like those images who are drawn from this similar cluster. So now as you can see, these particular images are drawn from this particular image anchor, and now when you try to increase the similarity, the representations will be so similar, and the weights of ResNet and MLP will be adjusted. We will learn more about this particular process when I talk about the training procedure. So before going to the training procedure, we'll look at the pair selections. So pair selections is very important for us, because using the pair selection, we'll be creating our training data. So as you can see here, there are two types of pair selections. One is self-supervised contrastive learning approach, and then one is supervised contrastive learning approach. So self-supervised contrastive learning approach is used when there is a no targets, when there is an absence of targets. And supervised contrastive learning will be used when you know the targets. So now let's go to self-supervised contrastive learning, where initially we will take a particular image and we'll consider that as an anchor. And now we augment this anchor and create a new image called positive sample. Since we are drawing this, or we are deriving this positive sample from this anchor, it is wise to assume these two images are coming from a single cluster, and we consider them as a positive samples. So since we already have a positive samples, now we need to create the negative sample set. And we don't have the label information, so So what we will be doing, we will be randomly selecting the images from the batch we have, and we will consider them as a negative samples. Once the positive samples and negative samples are generated, then we will apply this, we will perform the same procedure that we have seen. We'll pass those pair informations to the ResNet and MLP, and finally try to create the similarity between them. We will try to increase similarity between the similar images. During that process, we will end up creating a representation for each and every image we have in a batch, and this process will be done for each and every batch we have. So, but there is one limitation in self-supervised contrastive learning, which is when you randomly draw the image samples for the negative samples, then we may end up having a positive sample in the negative samples, which will create a lot of confusion in the representations. This adds an error in the representations, but this is a limitation we have. But when we try to pass these representations to the downstream task, like a classification or a clustering or a image segmentation or or image detection, then these error will be reduced using those downstream task neural networks. Now, coming to supervised contrastive learning, unlike a self-supervised contrastive learning, we will be having labels over here, so we won't be having any limitations that we have faced in self-supervised contrastive learning. So we can easily able to create pairs with the label information, and we can easily able to generate the negative samples as well using label information. Once our positive pairs and negative pairs are generated, then we will again use the same procedure that we have discussed over here, and we will generate the representations. Since there won't be any limitation, since our pairs are drawn based on the known information, which are labels, then our representations will be so pure, and we can easily able to use them for the downstream task without any error. So now coming to the pair selections, in supervised contrast to loss, we can only create one positive sample because of lack of labels, and can create many negative samples if we are randomly selecting it. But in supervised contrast to loss, we can have many positives and many negatives because we know the target. Since we know the target, we can easily go ahead and pick as many number of positives and as many number of negatives based on the batch size we have. Now, coming to the training procedure, here we have three different types of trainings. One is a supervised learning, which everybody knows. I guess most of you also know. And another one is self-supervised contrastive learning. Another one is supervised contrastive learning. So supervised learning is majorly used in our real-time world, and it's a traditional way of classifying the images, where you pass a certain image and to encoder, and you classify them using a cross entropy loss. So since it's a very traditional way of classifying the image, I'll not focus more about this particular thing, because our major topic is contrastive learning. So I'll focus more on these two training procedures. So in contrastive learning, there are three major steps. One is data augmentation, encoder network, and projection network. So in self-supervised contrastive learning, we need to do data augmentation because we don't know what is the label. So in those cases, like I mentioned in the previous slide, to create the pairs, we need to have an anchor and we need to create a positive sample. So for that, we need to create an augmentation. We need to augment the anchor and create a positive sample. So for self-supervised contrastive learning, we need to create a data augmentation. But in supervised contrastive learning, we don't need to do any kind of augmentation. Even though you want to, you can, but majorly we won't be needing any data augmentation to create these pairs, because we already know the labels. We can draw positive samples from the same target, and also we can draw negative samples based on the label information. Now, once the pairs are generated, we will be passing these pairs to the encoder network. This is the encoder network, and this gives us certain representations. Encoder network is nothing but a kind of ResNet, which we discussed before, the function f. And this ResNet will give us certain representations based on the previously learned weights, and that representations will be passed again to the projection network. So now this projection network is nothing but the MLP, multi-layer perceptron, and the representations of encoder will be passed to the projection network, which is MLP, and projection network again gives us certain another set of representations of images. Now, these representations will be used for contrast to loss. Like we pass these representations to the contrast to loss, because when I mentioned contrast to loss, it is purely depends upon the contrast to learning approach. So I'll talk about this contrast to loss, but I'll tell you like what exactly this contrast to loss does. So when you pass this representation to the contrast to loss, it tries to increase the similarity between the images, similar images, and it tries to decrease the similarity between the two different images. So based on that concept, we will be training our model. We'll train our encoder model. We'll adjust our encoder model basically, because in this case we are using ResNet. So ResNet already has certain pre-trained weights, but that is not purely trained on our use case, on our labels. So what we do, we use contrastive learning to adjust the ResNet weights, and will create certain representations which is suitable to our use case. So contrastive learning does that. So in supervised contrastive learning, we know the labels. So we accordingly increase the similarity for those images which are taken from a single class, and will decrease the similarity for those images which are taken from a different class. So once the training is done, then we will have representations according to the labels we have. Then we will pass those representations for the downstream task. In our case, it is a image classification. So we use representations that we have, and we'll pass to some dense layers, and finally we use cross entropy on top of it, and we'll classify the image. So in supervised contrastive loss, here we are using contrastive loss initially to create the representations, and at the end we will be using cross entropy to classify the image. So one more thing to highlight over here is it is not only used for image classification. You can use the representations for any kind of problems we have. We can use for image detection, you can use for image captioning, you can use for image segmentation. So it can be used in any use case, like it can be used to solve any kind of problem. So finally, we will apply cross entropy, and we will classify the image. So these are all about the training procedure. Now we will see what exactly a contrastive loss is, because we were discussing a lot on increasing the similarity and decreasing the similarity based on the images that we have drawn from a single cluster, and also on all of those things, right? So we'll just see like what exactly these loss is all about, and how we will increase the similarity and how we will decrease the similarity. So we have two different losses over here. One is a one is a supervised contrastive loss, and self-supervised contrastive loss. Another one is a supervised contrastive loss. So if you look at these two losses, both the formulas are little similar. Both the equations are little similar, but supervised contrastive loss is an extended version of self-supervised contrastive loss. So I'll talk about these two, and also tell you like what is the major difference between these two in a while. But first of all, we'll try to understand what exactly this loss is about. So now, as you can see here, we have in numerator we have z sub I and z sub j. Z sub I is nothing but the anchor representation, and Z sub j is nothing but the positive sample representation. So since we have self-supervised contrast loss, since we are talking about self-supervised contrast loss, we only have one positive sample like we discussed before, which is one anchor and one positive sample. So we'll try to understand the similarity between anchor and positive sample, and we'll try to increase that similarity. And the denominator is rest of the things. So we'll try to check the similarity between anchor and the rest of the negative samples, and we'll try to reduce this similarity. So the numerator is supposed to be higher and the denominator is supposed to be lower. And we have a negative symbol which can be used for loss. The higher the numerator, the lesser the loss will be. So now in this way, we'll be able to increase the similarity of a similar image and decrease the similarity of two different images. And exponential and T are the normalization constant. T is nothing but the temperature. In implementation, we'll pass some value to this so that we can normalize the values. And exponential is another normalization constant. We will just normalize the value we will be getting from the dot product of these two. And coming to supervised contrastive loss, here the only difference is this particular part. When I mentioned supervised contrastive loss, that means we know the label information. So when you know the label information, like we discussed before, there can be many positives and many negatives. So when we have a many positives and many negatives, we have to adjust the loss functions according to that. So for that reason, what we are doing, we are introducing this particular condition, which says the label of P equal to label of I. So when you look at this numerator, it says any representations whose label is equal with the P, then we will increase that. If you take this Z sub I label, if in case the Z sub I label is equal to the Z sub P label, then we will try to increase that particular similarity. If not, we will reduce. So whatever, like if the label is similar, then the numerator will try to increase the similarity. If it is not similar, then the denominator will try to decrease the similarity. Similarly, we will have a higher numerator and lower. We'll have a low denominator, and remaining everything is constant. So the only difference between these two is here in this supervised contrast loss, we are passing some label information. It's a kind of prior knowledge to the loss function. So this is how we create the contrast to loss equation, and we'll be using this particular loss in our training procedure. So I'll quickly walk you through the code. Let me just share my screen. I'll just stop my screen share. I'll share the another window. Um, just a minute. You are able to view my screen, right?
Yes, sir. We are able to see it. Yeah.
Yeah. So here I have two different experiments. The first experiment is a traditional way of classifying the images, where we use a ResNet and we will create a classification layer on top of it. And another one is using contrastive learning. So first we will see the traditional way of approach, and we will observe the test accuracy, and also we will see the contrastive learning approach, and we will observe the test accuracy. Now, in the first cell, I'm just importing all the libraries that I need. And in the second cell, I'm just loading the data. Here, the data I'm considering is CFAR 10 with a 10 classification with 10 classes, and the input shape is 32 cross 32 cross 3 three-dimensional array we have, and sorry, and we are splitting the data into two different parts. One is for training, another one is for testing. The training data contains around 50,000 images, and the testing data contains around 10,000 images. So once the split is done, then we are augmenting our data. And before the augmentation, I'm normalizing the data, because it is important in deep learning for us to normalize the data to converge the things faster. And after that, I'm using some random augmentations, so that we can add some error and we can avoid the overfitting. So I'm just adding a layer, data augmentation layer. After that, I'm creating an encoder. What I'll do, I'll just quickly open the training process so that you can easily able to correlate. So initially we have this encoder network. So I'm just trying to create this encoder network over here. So in encoder, I'm using ResNet. So here you don't need to only stick to ResNet. You can use any kind of pre-trained weights. If in case you want to go for some advanced pre-trained models like EfficientNet or something, you can use it. Not a problem at all. So here I'm just using ResNet 50. And ResNet 50 will give us certain embeddings based on the previous learnings. And we pass the input to the data augmentation initially. So if you can see here, I'm creating an input layer and I'm passing those inputs to the data augmentation that gives me augmented images, and those augmented images are passing to the ResNet, which gives me certain output. Now that output I'll be passed as an features. So as you can see here, let's go to the summary of the model. I'm passing an image having a shape of 32 cross 32 cross 3, and the ResNet gives me 2048 different dimensions, and I'll be using these dimensions for my classification. And also coming to some of the hyperparameters I'm using learning rate, batch size, hidden units, number of epochs, and dropouts. So learning rate is 0.001, and the number of epochs is equal to 15, and the hidden units are 512, and the batch size is 32. And now coming to the classification layer, I'm just creating a function for classification model. This is a traditional way of handling the image classification. As you can see here, first I'll create an encoder, and I'll add a classification model on top of it. That is what I'm doing here, because it's a traditional way of classifying the images. So in this classifier, what I'm doing, I'm just keeping the layers for training, because we need to adjust the layer weights according to the cross entropy loss we have, according to the targets we have. So I'm just keeping the trainable equal to true. And like I mentioned, I'm just taking the features from encoder, which is around 2048 different dimensions, and I'll be passing those features to the dropouts and some dense layers. And for dense layer, I'm using activation layer as ReLU. Activation equal to ReLU for this dense layer, and at the end I'll be having another dense layer with activation softmax. Since it is a multi-class problem, we need to use softmax. And at the end, I'm using optimizer as Adam, and the loss is sparse categorical cross entropy, and the metrics is sparse categorical accuracy. So we have created the classification model. Now what we do, we just need to train the model. As you can see here, I'm just initializing the encoder, and the encoder values will be passed to the classifier, and the classifier model has been created. And if you see the summary of the classifier model, initially we are passing the input, and that input will be passed to the encoder, which gives us 2048 different dimensions, and those 2048 dimensions will be passed to the classification layers and the dense layers we have, and finally we'll be having 10 different outputs, one probability for each class. Now we'll be training this data for 50 epochs, and as you can see here in fit, I'm passing xtrain and ytrain, and the training has been started. And actually, I executed all these things before because it takes a lot of time for us. I executed this on GPU, so it took some time for me. And at the end of 50 epochs, we have the test accuracy as 80.5%. Now, this is a traditional way of solving the images, which most of you might know about this. Now we will look at the implementation of contrastive learning, and I will see how we can implement and how that can affect the results. So initially, I'll just install the TensorFlow add-ons because to build the supervised contrastive loss function, I need the TensorFlow add-ons because that has certain libraries that we need. And I'm importing the libraries that I need. And as we did earlier, I'm loading the CFAR 10 data. Here, what I'm trying to do for comparison, I need to make sure everything is same in both the experiments. So I'm just taking the same data over here as well, and the number of classes equal to 10, and the input shape is same as before. And the training data contains 50,000, and the testing data contains 10,000 different data points. And again, I'm doing the data augmentation, adding a normalization layer in a normalization layer before, and having some augmentation layers after that. And once that is done, now we need to build a loss function, which is a supervised contrastive loss. So this is the loss function that we'll be using. I'll just quickly help you understand what exactly happening inside this. So like, let me show you the equation parallelly. So like I have mentioned, there is one major difference between these two, which is passing the labels, and also we have something called dot product of representations. So for this particular equation, we need two different parameters. One is representations, another one is label, and also temperature constant. So now, as you can see here, we are passing one way, parameter, which is temperature, and also two different other parameters. One is labels, another one is feature vectors. So these feature vectors are nothing but the representations. And now we'll perform some math multiplications and pass the logits to the n pair loss. So n pair loss is nothing but the loss of self-supervised contrastive learning. So in so like I mentioned, here the major difference is passing the labels. So I'm just passing the labels to it, and along with the logits we have. So here what happens, this particular loss function will take care about the similarity. It will just increase the similarity for those images which are more similar, and it will decrease the similarity for those images which are totally different from each other. So this loss function will help us with that. And now we'll create an encoder. Let me open the architecture again. So we will create an encoder. Here, as you can see, again, I'm using ResNet 50, and I'm passing the inputs to the data augmentation part, and that gives me some augmented images. And those images again pass to the ResNet, that gives me an output. Now, there are few more hyperparameters in this, apart from the hyperparameters that we have used earlier in the experiment one, which are projection units, which is 128. And the batch size is changed because here from the paper, I learned that higher the batch size, the higher the improvement, because if you increase the batch size, then there will be many positive pairs and many negative pairs to create. So it is good to increase the batch size. Previously, we used batch size equal to 32, and here we are having a batch size equal to 265, though it consumes certain memory with respect to CPU and GPU, but it is always good to use a higher batch size. And you can play with these hyperparameters. So I'm actually taking the very basic hyperparameters. I haven't do any kind of hyperparameter tuning. Just for the experimentation purpose, I have randomly taken certain hyperparameters. But if in case if you want to learn more about this particular contrast learning and want to see the capacity of this particular thing, then you can play with these hyperparameters as well. You are welcome with that. You can do certain pet projects with that too. Coming to the summary of the model, we are passing the input, and we are having a 2048 different dimensions from the ResNet. And now we will be creating another network called projection network. Like I mentioned in this particular slide, we have three different parts. One is data augmentation, encoder, and projection and network. So these two are already done. Now we need to create a projection network so that we can train this particular model using contrast loss. So I'll be creating a projection head over here. So here we are passing the encoder input. We are passing the inputs to the encoder, and the encoder input will be taken as a features. And now we will just concatenate both encoder and projection head so that we can train our model. So as you can see here, I am initializing the encoder part, and the encoder information is passed to the projection head. But the major thing that you need to notice over here is the loss is changing over here. The loss is supervised contrastive loss. Optimizer is Adam as always, but the loss is changing. Now I want to take you to the loss again, because here in the summary, as you can see, we are passing the input, and the input is passing to the encoder, which is giving 2048 dimensions. And when you pass those encoder outputs to the production network, it gives you 128 different dimensions. So these 128 metrics, 128 array will be passed to the supervised contrastive loss. So the feature vectors which I mentioned over here as the representations, those are coming from the projection head. So as I mentioned earlier in the training procedure, the representations of projection network will be passed to the contrastive loss. So the same way here also in the implementation, the feature vectors are coming from the projection network. As you can see here, these 128 dimensions will be passed to the supervised contrastive loss. So now once the model is initialized, then we will start the model. And I have chose 50 epochs for this, and we are passing the features, I mean image arrays, and also the labels. The reason I'm passing the label, because the supervised contrastive loss needs the label information, so I need to pass the labels as well. So now we will initialize the training procedure, and the training has been started. And if you can see, initially the loss is 5.3664, and at the end of 50th epoch, the loss got reduced to 3.74. So this tells us that um, we are able to learn certain representations based on the targets we have. So what happens during this process, the resnet will be adjusted. Since we are concatenating the encoder and the projection head, the resnet weights will be adjusted in a such a way so that it gives us the representations according to the labels we have. So now we have the representations that we need, and we will pass those representations to the classification model. This is the same classification architecture that I have used in the previous experiment. Like I mentioned before, I am using the encoder layers, and I'm keeping them as trainable because we need to adjust them again based on the cross entropy loss. We already adjusted them using contrast to loss, but we want to adjust them even more using the cross entropy loss. So I just kept them trainable equal to true, and we are passing the inputs to the encoder, like I mentioned before. Now the adjusted representations will be taken into consideration. In the previous experiment, we were just using the same representations that encoder generally gives us, but here in this case, we are using the representations which were adjusted using contrast to loss. So those representations will be used here, and now we'll be passing them to the dense layer with the ReLU activation, and the final dense layer with the softmax. And this gives us the probability, where the optimizer will be Adam again, and the loss function is sparse categorical cross entropy, and the matrix is sparse categorical accuracy. And we will start the training, and the batch size will be 256, and the number of epochs will be 50, and everything is similar. We have done everything just like the way that we need to do. It's a normal traditional way of training the model. So as you can see, after 50th epoch, and the number of epochs are 50 in this particular case, as you can see at the end of 50th epoch, the test accuracy is 81.52%. So previously in the experiment one, our test accuracy is 80.5%, but using contrastive learning with 50 epochs, our accuracy improved from 80.5 to 81.52. So we can see a significant improvement in this experiments with using some basic hyperparameters. If you can tune more, and if you can add more layers, if you can add more augmentation techniques, if you can regularize them better, then you may end up even creating a more robust model than what I have right now. So the ultimate conclusion over here is the supervised contrastive learning outperforms the traditional way of classifying the images, and also it can be used in any kind of downstream task like classification, image detection, image segmentation. Also, it is widely used in natural language processing as well. So it is good to learn the representations over here. and it will adjust according to the use case we have than having a generic embeddings. So that has been said. Now we have gone through the code as well. Now I'll take few questions if you have any. I'll just stop sharing my screen. If you have any questions, please feel free to ask.
I would like to tell hello. Sorry, I would like to tell the attendees that there is a feedback poll I have put in the poll section. If you can give it, that will be good
Cool.
to all the attendants. Yeah.
Thanks, Shram. Yeah, definitely. I have shared the sample code with the team. Maybe the team can share those snippets with you. And also, I will share the research papers that I have considered to put together this concept. Maybe people can share that as well, if I'm not wrong. Tejas, you can share with them, right? If I'm not wrong. I guess I have involved everything in that deck I have
Uh,
shared with you.
okay.
Uh,
The mail, right?
yeah, mail.
Okay.
I
Can
can
you
share
only
here,
share?
but
Yeah.
yeah, let me try sharing the snippets that I have.
Yeah. You can share it
I
here,
can
I think.
I can share it here, right? Yeah,
Yeah.
let
Yeah.
me try
In the
sharing.
chat section, maybe. Yeah.
Yeah. Yeah, I share the code snippets with you, and I'll also try to share the research papers. Somyajit, sorry, I might have missed it. Can you please post your question again, if you don't mind? Oh, okay. There is a separate session for Q&A. Cool. What are the data augmentation? I'll just go from one. I guess I didn't check this Q&A part. I'll just go one by one. What are the data augmentation techniques for similar kind images in different classes? You can try. There are a lot of augmentation techniques we have. It's not like you can just follow one certain data augmentation every time. It depends upon the type of data you have and the domain you have. So you can try multiple techniques like blurring the images or rotating the image. It really depends upon how the quality of images you have, what kind of quality of images you have. And coming to the other question, what are the data augmentation techniques for similar images? Seems like the same question. Yeah. Uh, in slide 4, is the representation similarity between H and HJ also maximized? Okay, let me go to slide 4, um, and I'll try sharing my screen again. So I guess you're talking about HI and HJ, right? Yes. So when you try to improve the similarity between these two, and these two will also be adjusted. Once if you like, it's a kind of back propagation here also. Like function f and g will also be adjusted. If those are adjusted, then HI and HJ will also be adjusted. And let's go to the question. No, it's not a high dropout. Basically, zero 0.5 is normal according to my knowledge. Maybe you can try with different dropouts as well. Maybe you can go for 0.2 or 0.02. Bihi Saveri, I already shared the notebook, and I'll share the PPT as well in a while. Yeah, Riktesh, you can do sentiment analysis as well. Ultimately, whatever the use case it might be, you need certain representations based on your target. So you can go ahead with sentiment analysis for images. Sumajit Bera, I'm not sure what kind of problems you're talking under telecommunication, but if it is purely related to machine learning, yes, you can use it. Dinesh Singh, coming to contrastive loss, like I mentioned before, classification can be one use case, clustering can be another use case, image segmentation, image detection can be another use case. Like somebody mentioned, Riktesh has mentioned sentiment analysis for images. You can do that also. These are some of the best examples that I can give right now. But according to your problem, I'm sure you can use those contrast to loss anywhere, even for structured data. But also, if you have highly imbalanced data, that can also work over there. For fraud detection or for recommendations, no matter what kind of problem it is, embeddings are always needed. So you can use contrast to loss over there as well. Somnijit, I guess you asked multiple questions. Can this finding the problems in hardware authentication? So, Somnijit, can you just give more information about it? About this? What kind of data you will be considering, and whether it's a classification or something? Can you just give more information about this, Somnijit? I'll just wait for your question again. Somebody asked on Kaggle, probably 2021, there was a competition to find similar images from a web shop. Would it a valid approach to use contrast to loss there? Yeah, yeah, definitely. You can definitely use. You can try contrast to loss, and you can find out the similar images as well. Any other question? Meanwhile, I'll just share the PPT that I have over here. Sorry for coughing a lot. I shared the PPT. Thanks, Kishore. I'll just wait for a couple of minutes. Maybe if anybody has any other questions, maybe you guys can post it over here. They just, do I need to type the answer over here?
About
Or
what?
so because I could see an option to type the answer, do I need to type the
Yeah,
answer as well,
but
or
you
I
have
just,
told it vocally. That's okay, right?
that's fine? Okay, cool,
Yeah,
cool.
that the guys have said thank you and all, right?
Yeah, makes sense. Makes sense. I'll quickly share the research links as well, research paper links with these people. So this is one of the research paper that you can find on supervised contrast to loss.
Ashok sir, you are on mute, I think.
Yeah, sorry, I was coughing. Sorry about that.
Sorry. Yeah, okay. Sorry.
Yeah.
I think
So
somebody said that PPTs and codes are not visible.
is it? Can you check that?
Yeah,
Because I already shared
somebody
with them.
said, I think.
Let me try
Yeah, yeah.
accessing them from my end too. Um,
I'll just check once.
sure, 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 definitely.
The link that you sent right now, right?
Those are research paper links, but
Okay,
I
okay.
already shared the files with them. Let me cross verify from my end. I could see, I could see them. Do I need to share them again? Who asked it?
Yeah, do that also. If he can't
Yeah,
see, maybe he can see right now if
yeah.
you said
John,
it
if you're
once
not
again.
able to see, let me share them again. John, I have shared. Please acknowledge if you're able to view them. Thanks, Sita, for confirming. John, can you confirm as well? It just seems like nobody
Yeah.
has any questions. Maybe I guess
Uh,
we
okay
can
then.
just drop off, I guess.
Okay, then I'll thanks a lot, Ashok. On the
No
behalf
issues.
of on the behalf of Analytics Vidya, I would like to thank you for delivering such a wonderful session. I'm sure that everybody is insightful and hopeful that so that we can conduct the more sessions with you in the future. The LinkedIn ID of Ashok is present in the chat window. If uh, everybody can see it right there. I hope that you have filled up the feedback poll, and if you have not filled it, please fill it because it helps us to conduct more such sessions. Uh, if you wish to conduct a webinar or are facing difficulty in registering it, connect us with at data@analyticswitha.com. The recording of the session is available in 2 days on our YouTube channel. The link is present in the chat section, and we will be back for with another session on 11th of March, another data session. The link is present in the chat sections. Till then, bye bye and keep learning.
Thanks everyone for
Awesome.
joining
Thanks,
again.
Ashok sir.
Thank you. Thank you very much.
Thank you very much. Thanks everybody.
Yeah. Bye bye.